Assalamu alaikum. Welcome to CFD tutorials. So today we are starting with the first example. We will be using two softwares in this lecture series or in this tutorial series. We have ANSYS Fluent and COMSOL Multiphysics for the CFD softwares. And first example will be a simple example for Venturimeter analysis. So we will do CFD simulation of the Venturimeter. And I hope that we will have a couple of good examples, good tutorials. And ANSYS Fluent users or new learners, as well as COMSOL Multiphysics new users or current users, I think can learn too many things from these tutorials. If you also consider to switch from one software to other software, actually, and I was also thinking to do this, I think merging two different softwares in one tutorial will be helpful to understand the difference between two softwares and have a better understanding or broader understanding in different CFD softwares. So let me start by introducing myself. I'm a mechanical engineer. I got my bachelor's degree from Gaziantep University, then my master's degree in also mechanical engineering in Istanbul Technical University. And my CFD interest actually in this field, like thermofluids interest, started from early times of my bachelor's, but after I started my master's study at Istanbul Technical University, I focused more on the thermofluids like fluid dynamics and heat transfer and also computational methods. Then now, currently, I'm a PhD student at KAUST at Saudi Arabia, and I'm working in a chemical engineering department in the multi-scale reaction engineering lab. So my research also here focuses on the CFD simulation of the reactors. My previous experience in the CFD actually consists of different kind of projects, industrial and academic projects, and also some theoretical simple projects. I can mention that it was useful when I did my master's coursework in Istanbul Technical University to get not too much deep, but to understand some basics of CFD solvers. So we used finite difference method, and we were programming ourselves to solve simple fluid mechanics problems. So this problem, for example, is a lead-driven cavity, is a simple fluid dynamics problems for new learners how to code for CFD. But it's just to understand how solution algorithms and how meshing quality and initial prediction or initial condition when you put in the solver affects the solution quality or performance or sometimes convergence and divergence of the solution. This is a multi-phase flow simulation for thermoplastics, and this is validation of a design for an industrial company for a valve, balancing valve product. So let's start by talking about CFD. Actually, I think I will try as much as possible to simplify and to make this journey easier for you. But let me be honest at the beginning that CFD, becoming a CFD engineer or as a design engineer, if you want to become a design engineer, you are already a design engineer, but you want to learn this tool. It's not an easy journey. Or if you are in the industry, or if you are like me working in the academy, so it's not easy to learn CFD, how to do it by even commercial softwares. Even if you don't get deep into how to code, how to use finite volume method, how to code yourself to solve heat transfer or fluid dynamics problems. I think even by using commercial softwares, it has a lot of troubles when you are doing your CFD, because it consists of three like complicated parts, I can say. 3 complicated main parts, like geometry, solver, and physics. And sometimes you have a lack of information in one. Actually, at the beginning, we have always like lack of information in 3 of them. We don't know like 3 of them. We have mistakes in the 3 of them. And by time, we like troubleshoot. So you see that like I like as an engineer and like as a self-learner, I can mention like I'm a self-learner. I always learn things from YouTube and from forums, from other kind of like sources. I can say that my learning journey, like for coding Python or coding MATLAB, like image processing or something else, like related to engineering or technical skills, was easier than CFD. CFD was always the hardest one. So you see that CFD, like learners, like they are a community. So they always like communicate with each other and like ask questions. From a couple of years, actually, it is like this. You will see, like sometimes your problem can be like answered 10 years ago in a CFD forum. So it is good to mention at the beginning that it's a not easy journey, but I will try to do my best and simplify as much as possible. And actually, as I mentioned, that I'm a self-learner, and I saw some tutorials in YouTube, and I saw like I get benefit from a lot of tutorials, and I learned a lot. And I realized that there are some missing parts, or sometimes that watching this tutorial is not helping me, because very simple examples, and I want to do something like more complicated. Or I want to like validate, I want to reproduce published CFD results. I see an article, journal article, I want to do the same simulation. So how to do this? So actually the first tutorial, we will try to reproduce a result from a journal paper, and we will like try to extract the useful information from that paper. We will like briefly summarize it and read it together. So I think you can also watch other tutorials and other sources. It's like I said, this is a long journey to learn CFD. You will like combine multiple sources, but I think also this source will be useful for you. And I plan to repeat our live sessions once per 2 weeks, or sometimes once per week, sometimes once per month. But as well as I have some like followers that want to like continue in these sessions, it will actually encourage me to do more. So I'm happy that today in the live session some friends joined us, and I hope also recording will be helpful for other students or learners. So let's start by the geometry. So what we need for the geometry? Usually, actually, this is the main part of, I can say, like we have 3 main parts. I cannot separate them, but so you start usually by the geometry, and sometimes you start thinking about the physics, sketching something. So you also sometimes start by thinking about the solver and physics by together. So there is nothing like you should start by this first or other. So you should have understanding of all of them. So you decide what to do. Sometimes like best way to get a paper and sketch your problem, understand the physics, which models I need, which solver is best, which software I should use, and so then convert this sketch into a geometry. So your geometry can be a 2D geometry or can be a 3D geometry. Sometimes it's 1D, sometimes 0D. Sometimes in the sketch you will realize that I don't need a CFD simulation. I can just use 1D correlations, just empirical correlations to simulate my problem, my physical problem. So it's very recommended to start like sketching, thinking about your physics. Sometimes you don't need CFD. Your problem does not require CFD. So after you get sure that your problem is requiring CFD, like we pick up single phase flow, for example. I want to simulate like an airfoil. I want to investigate the lift forces, okay, and coefficient of drag. So I don't want to get the entire wing geometry, okay? It is just a like cross-section view of this wing can help us to understand the coefficient of drag and lift forces. We can extract a lot of useful information. So to simplify the geometry, to simplify the meshing, to simplify our solution, you see a lot of things here, solvers. So to simplify the computer's work, you can simplify your geometry to have a 2D solution. So let's say we have single phase flow, only air is flowing, okay? So you like define your geometry, what is my domain? Sometimes you need enclosure, for example, here you have a solid, it will be your wall. You have an air, but when you stop your air domain, when you stop, you need like to have some enclosure, like a wind tunnel, like think about a wind tunnel. So you should like have a tunnel to like understand like what is the maximum distance that airfoil's disturbance in the fluid domain affects. So you should enclose that area and include in your 3D model or 2D model. So this is basically explaining some ideas of geometry. So we need CAD models. Sometimes we will model them in the software itself, commercial software itself. Sometimes we need to, like if it's challenging to model there and you are more comfortable with other like SolidWorks or Siemens NX or CATIA. So you can also model your 3D model in other software and import your file into the software. When it comes to solver, numerical methods, actually these are working, you can search to have a simple like general idea about finite difference method. It is the easiest solver for structured meshes, for like easy problems. So you can start by FDM and have an idea. So we have also physics. Let's start actually mention step by step. For CFD geometry, what we can do. At the beginning, at the first step, we model the CAD. We can use, as I mentioned, SolidWorks, CATIA. Your geometry can be also 3D scan data, or it can be a very simple geometry, okay, like primitive shapes. Secondly, you do domain simplification, or sometimes actually you don't model. Like usually, CFD engineers in the industry, like they are given some CAD files. They do not do CAD. Usually, there are some CAD engineers or like technical drawers. So sometimes, like if you want to become a CFD engineer and you say, I don't have too much design skills, I cannot do CAD, don't worry. Just usually, a CFD engineer starts from this step, clean up and repair. So takes this geometry and repair, and maybe even simplify it more than this. Like you remove the bolts, screws, you remove the sharp edges or some unnecessary like chamfers or fillets, or you add some chamfers and fillets sometimes. So you simplify your geometry as much as possible to like reduce the load of the computer. Okay, you want to solve the problem. Like there are some unnecessary details in the CAD file. You don't want to take, like I have this geometry, I don't want to take this geometry and put it in my software. I want to simplify. I don't need, like, I can simplify it in the CAD. The model can be more simpler than this, and solution can be more simpler, but also it can simulate this exactly. It can simulate the real case by changing the 3D geometry by some cleanup and repair steps. So after that, you extract your volume, because you don't want to solve anything about your solid. If you are not interested in the solid domain, so you are not doing a structural analysis, you are doing just fluid dynamics, a pure CFD solution, like by heat transfer also sometimes included. But let's say we are doing like single phase fluid dynamics problem. So we need to extract the volume inside, because the fluid will not be solved. Only the internal volume of the water or any fluid will be like our interest. Then we have the computational domain, the fluid volume, as it mentioned here. 2D domain surface can be like this. You have wall of the solids, and you have the enclosure, you have inlet and outlet. And 3D domain can be like this. Okay, you have inlet, outlet, slip walls, and also non-slip walls. 1D study, as I mentioned, sometimes you don't need to put your solution. Like you can also use like COMSOL Multiphysics, for example. It solves also some 0D, 1D problems. But there are some other tools like MATLAB Simulink. MATLAB Simulink is a good software for solving 0D, 1D problems. So if you are sure that you don't need CFD, you go to 1D modeling. You can search also for this, 1D modeling. Okay, so 1D modeling for heat transfer, for example. 1D modeling for cooling of an electrical motor, for example. 1D modeling for a cooling of an electrical motor. So it's very useful, and it's very, like, sometimes you have some engineers working only in the 1D modeling, doesn't know CFD or like not skilled in CFD, but it's more useful for this company to simulate the complicated system in 1D empirical correlations to predict what happens, and it gives a very good prediction actually when you have 1D model. So keep in mind that there are some alternatives of CFD. Sometimes your solution doesn't require CFD. What about the CFD solver? I actually really encourage you to learn something about like a finite difference method. I think this is the easiest one, finite difference method. But ANSYS Fluent uses FVM, finite volume method, and COMSOL FEM, finite element method. And we have also some FEM modules in ANSYS itself, but not for fluid dynamics. When you have heat transfer in solids, like usually for solid domains, we use finite element method, like structural analysis. And FDM also, as I mentioned, you can search about it. I mentioned that I coded by MATLAB by using finite difference method. This is like a flow of air in a cavity lid. It's like, this is the name of the problem. So you can understand, not necessary to code by yourself, but just understand like that you are converting your physical model. You have a mathematical equation, like you have governing equations, PDEs usually. Navier-Stokes, I think you are familiar with Navier-Stokes. You heard about this equation, right? Navier-Stokes from your bachelor's fluid dynamics course, Navier-Stokes. So you are solving Navier-Stokes in CFD, and you are solving energy equations for heat transfer simulations. So get aware what are the equations behind of the software. Don't get deep too much, okay? It's not the target. If you want to like become a practical CFD user, not necessary to get too much deep. By time, when you need, you will learn more and more. But so I think it is enough for to mention for finite difference methods. So numerical algorithm also, there are some things inside of the like code, how it solves your problem. You have different algorithms, okay? For example, your time integration can be implicit or explicit. Explicit means you are calculating next step directly, and implicit means you have a matrix. Sometimes this matrix can be like million to million, okay? Your linear solver can be million to million matrix, so you are solving a huge problem, and sometimes more and more and more. Meshing also is important. We will also start meshing our 3D. We will model 2D and sometimes 3D, then we do meshing. Then because you are solving in the elements, your like this governing equation is being solved in these tiny small elements, okay? So be aware of these components. And when it comes to CFD physics, we have the core of the CFD is the fluid dynamics, okay? So usually we have the flow inside, okay? So you should be like a good user, or good, like you should understand fluid dynamics well in order to like become a good CFD engineer. So you understand the governing equations, you understand the flow regimes, like we have turbulent flow, we have laminar flow, okay? You understand some like ideas of what's turbulence modeling, because you are selecting some of the models in the software. In ANSYS Fluent, also in the COMSOL, we will select a turbulence modeling, but based on what? Sometimes in the laminar flow, we don't need turbulence modeling. We just select laminar flow and solve the problem. When it comes to, like, as I mentioned, you sketch and you understand your problem. Do I need heat transfer? For example, let me mention my CFD project that I worked on it. This is a balancing well for a water, okay? And it's at the room temperature, okay? And there is no rotating parts. That like you are not doing like any thermal effect on your water. It's just pure hydrodynamics, okay? So you don't need to use heat transfer here. And there is no phase change, okay? Like water is not evaporating, or not, there is nothing like other phase included inside. So that simplifies your physics. No conduction, no heat transfer, and also no phase change. You have only one phase, single phase fluid dynamics. Okay, it can be also multi-phase flow. It's actually more challenging than like if you have like a boiled water flowing, for example, a boiled water. So it includes vapor phase and liquid phase and flowing inside of a channel. How to solve this problem? It's more complicated. You have some methods like volume of fluid. And other coupled physics, like you want to simulate the combustion inside of an engine. Okay, it can be gas turbine engine. In the aerospace industry, it can be internal combustion engine. And if you want to understand the vibration in the wings, it will become a fluid structure interaction problem. You should understand this structural dynamics as well as coupling it with your fluid problems. You need electromagnetics sometimes, you need acoustics. Electromagnetics, for example, for the electrical motors. And acoustics, if you want to simulate, for example, I want to simulate this room. I want to understand what, where should I put the absorber, for example, for the acoustics. I want to minimize acoustic performance. I want to maximize it. Depending on the application, the room. Is it a conference room? Is it as a room that I make my videos, so I need a specific quality. So you can just enclose your room and you have a source. It can be a speaker, okay, of the laptop, or it can be speaker of anything in the conference room, for example. Is it reaching the audience? Is it reaching all of the people inside of the conference room? So you can do acoustic simulation, okay? Let's start by the problem. I talked a lot, but let's start. But it is the first tutorial for the CFD sessions. I'm sorry if I talk too much about some introduction, but we are starting now. Don't worry. We will open our software and start working. So this is our first example. This is from a paper. And what I like from this tutorial, and I want to include in as much as possible. Sometimes you cannot find. I searched a lot actually. I downloaded 10 journal articles, and I reproduced some of them. But I saw this is not good, this is good, this is better. I selected, I think, the better one. I like this one compared to other articles to have a good start. The good thing here, you can go through the paper, understand also the experiments. Because in CFD sector, you need testing. If you are a researcher also, you need to have if you don't want to do your experiments, you can have a collaborator in another country doing experiments, or another university. They are doing the experiments and you are doing the CFD work. Because without validation, CFD simulation, without validating, doesn't make sense. It can be wrong solution. How can we be sure that this CFD simulation gives us the right results? So we need experiments. So it's very good at the beginning to read some papers, include experiments and CFD simulations, and try to reproduce results of the authors. So you see here, we have a setup of nitrogen flow, okay? And it's also, okay, let me open some pictures for you. Okay. I don't know if I included here. Okay. Let me talk about Venturimeter a little bit fastly. Okay. You see that Venturimeter is a very useful tool. I think you have an idea about it if you got your fluid dynamics course in your bachelor's. It's a very good tool to measure flow rate. Okay. To measure the flow rate. And the flow rate, understanding what is my flow rate in my industrial, in my factory. I have a process, okay, or I have an air conditioning unit in a large building. What is the airflow? I should control, I should understand, I should measure, right? So in a lot of applications, you need to measure the flow, and there are several ways to do that, but Venturimeter is one of the simple ideas how to measure the pressure, how to measure the mass flow rate depending on the pressure drop between these channels. When you decrease the channel diameter, you increase the velocity, and there will be a pressure change, okay? Depending on the pressure drop, you evaluate the mass flow rate. Okay, it is basic Bernoulli principle. Maybe you remember it from the bachelor's. So this is our tube dimension. Okay, I want to mention that cast iron Venturimeter is a very huge, very large one. And you have plastic mini Venturimeter, sometimes stainless steel, very tiny, like very small tubes. You can measure air flow rate, you can measure nitrogen flow rate, you can measure water flow rate, you can measure some other fluids. So it's a very useful tool. It's a very useful measurement device. And there are some others like orifice meters or some other kind of flow meters. We will have also in another session orifice meter problem. So you see that we have a geometry, okay, it's a pipe. So we want to simulate this in 2D. Why? Because we can simplify it. I mentioned if you have an opportunity to simplify the geometry, you will prefer to simplify, okay? So let's start opening the software, okay? I will try to connect to another desktop, okay? And also I'm using my laptop here. So we will simulate, like we will try to go through 2 different softwares, okay? Here I will open ANSYS Fluent, okay? And in my desktop here, I will open the COMSOL, okay? And we will try to simulate the problem by using 2 softwares, okay? So let's start to understand what is the, like when you start Workbench, this is like how you start your simulation. You just download and install ANSYS, okay? Then you start by opening Workbench. Then what you want to do, there are a lot of models, okay? ANSYS is a very powerful tool. You can do a lot of things. I mentioned acoustics, I mentioned some different physics, okay? You can do multiple things here. But we are interested in ANSYS Fluent, okay? So we just take it, then drop it here. Then we start by geometry, then mesh, then setup. So I actually mentioned this, that we have a geometry, then we have mesh is important, then we have a physical understanding of the problem. What is our physics? What should I put in the boundary conditions, for example? How to solve? What is the physical condition? What is the inlet velocity for example, this problem? Let me open. So we will take this information from the paper that we put inside of the geometry. But let's start by just drawing the geometry. Just right click on the geometry, then open new space claim geometry, okay? So we start by drawing our 2D Venturi tube. I think it's better to switch from the, okay, you see, I think I have, okay, let's open the paper and see the dimensions because I will use it. So step by step we will draw our geometry, but you see that 2D section is revolved, okay? I will show it in the software. So it's like in the cylindrical geometries, only you take a cross section from a plane, okay? From the mid plane, then you take this 2D, you can simplify to have an axisymmetric solution because it's an axisymmetric problem. Sometimes it can be a pipe, but you have something like junction coming or out, like going out. You have a non-axisymmetric, okay, an asymmetric model, so you cannot do 2D. But in this problem, we start simple, then we go to more complex problems. But so in this problem, you can do it in 2D, okay? And I will show also how to do 3D, but let's start by 2D. So we opened our space claim. Now it's opened, okay? Now what to do? Okay, I want to look at the surface perpendicularly, okay? We can also draw it from this plane, X and Z, okay? Or we can do X and Y like this. But let's draw it in the XZ. Z should be above like this, okay? So we have the sketch, okay, we just put take a line, then start from 0, 0, okay, from our origin point. Then I will check what is the, okay, not from here, I will check from here, 247.6, but we need the radius, okay, because I will only take half of the geometry, okay, I will only take half of geometry, so it will be this number divided by 2. Okay, so, but I think I didn't put divided by 2. Let me, okay, 247.6 over 2. Okay, so we have the first section. Okay, this is the second part. Let me check. It comes linearly, horizontally, until it reaches, okay, I should look at here, it's more clear, okay. So it comes like 192, then this, until it reaches that position. It's horizontal, okay. So I will add this to this. So let me check. So it will be 439.7. Okay. Straight line. 439.7. Okay. 439.7. Okay. We should go again to okay. Okay, so now we just continue taking the line from this part. Let's check the angle and the dimension that we need. Okay, so it is 10.5 degrees. 10.5 degrees. Okay, let's go back. 10.5 degrees. So you will say 180 minus 10.5. Okay. Then actually we can specify the dimension here because it's given to 67.2. Okay, let's go back. Let's check the angle again. So it's dropped. Let's define it because it's changing if you are not defining it. Okay. Let's check this. If they are changed, okay, this is changed. For example, I should fix it. 247.6 over 2. Okay, so it is good now. We are going well. Just we will add an horizontal line here. What is the dimension of this? Okay, 148.56. Then we have 7.5 degrees. Okay. Okay, let's put some dimensions here before going. So is it true? Okay, this is true. Then we have the other dimension here, 376. You just click on the point, the other point, then take you see that so you should move the cursor to get the horizontal distance. Okay, so it is 376.8. 14. Then actually what we can do that we put, okay, let's continue now, but let's put the horizontal distance. What's the horizontal distance after this? Okay, it is, let me check. So it is 1/936. We go back to x-axis now. Okay, we come to here, we go back to x-axis. Then what we can do is defining this length. It should be similar to what we have here, okay? And which is 247.6/2. Enter, okay. So I think we have a complete geometry, but I want to also put my axis here because this is the axis symmetry condition point, okay? This is the symmetric boundary condition line. So I should also put this line. Okay, I think we are done. Let's check this link, maybe. Okay, the angles are defined. Let's arrange them a little bit better way. Okay. We did not put this angle. It should be 7.5. Maybe we remove this. Or okay, it's over constraint, maybe over constraint, okay? Sometimes you put more than what you need, but this is our geometry. So after I finish the geometry sketching, okay, it's similar to some other CAD tools. Sketching is just AutoCAD, you know, from the AutoCAD or some other sketching tools or some other CAD tools. Similar, but to be honest, I don't like Space Claim. I don't like I hate COMSOL's sketch interface. What I do, I have Siemens NX, okay? I go to NX and I do my 2D or 3D model, what I need. Then I export it to like step or STL file or something else, but usually a step file for 3D or drawing or DXF for 2D files. Then I import it and use it. But in this tutorial, what I like to do, like I didn't like to use Siemens NX because maybe you are a SolidWorks user, you are like, maybe you don't know any CAD software, but you want to learn how to draw in ANSYS because maybe this is the only license that you have. You don't have other license. So don't worry, we will also learn how to draw by Space Claim and by COMSOL, but it's not that much comfortable. Why? Let me explain. Why? Let me explain briefly. Because, my dear friend, this is a CFD software. The company that developed this software developed it based on cleanup and repair functions usually. Like, if you are doing a cleanup or repair, okay, you want to like erase the faces, you want to repair this geometry to be more suitable for CFD, you cannot do this cleanup, this repair in other CAD softwares. It's very hard to do. If you have a CAD file, you want to clean it up, you don't use SolidWorks or NX, it's a waste of time. Why? Because CFD CAD models, like modules, they are designed to do cleanup. This is the best functions that they have. But if you are drawing from scratch, from the beginning, I don't prefer to do in Siemens. I don't prefer to do it in Space Claim. But if I want to repair a geometry, I go to Space Claim. It's very good. It's very like powerful software to do repair. And usually CFD engineers do it in within minutes. You can convert this to this. It's very easy to repair the geometry. There are a lot of development that they made in the code to have good cleanup and repair commands. But in terms of CAD commands, they do not invest too much to make very nice CAD model, because they know that their powerful part is the CFD simulation part. This is what they do. This is the main function of the software. But it is also good to mention that it's not that much difficult. It's not that much complicated. Sometimes it's also easy to have the geometry by using ANSYS space claim. Okay, we finished the sketch. Then we put we press on the end sketch. Now our geometry is ready. You can look at the interface here to switch to structure. I want to see my structure. Is it defined as a surface? Yes. So I want to have a surface. Arda and Emir, my friends, you're welcome to the live session. I'm happy to see your comments and thank you for your subscription, Arda. Okay, so what we need else from this part? Do we need something else in space claim? Sometimes they just save the file and exit, but I see that in the CAD interface, it's easy to select your boundaries. You want to do any selection, it's easy to control. Sometimes I prefer to name the boundaries, the inlet boundary and the walls boundaries and the fluid domain by just using the software itself, using the CAD part itself. You can do it in the meshing part laterly. I will show it, but I prefer to do it here. How to do it here? You click on the thing that you want to name it. You press Ctrl G. Okay, you press Ctrl G. When you press Ctrl G, you should also go to groups part. A group will be defined. Let me delete again, and I define another one. Let me do it again. I click on something, then I put Ctrl G. A group will be created. I don't know if you can also create it by right clicking. I'm not sure. I'm using this shortcut. I don't know where to do it. Okay, so let's come back. Okay, we hide it. Let's come and okay, let's come to groups. Okay, I want to rename it, not hide it. Okay, this is the axis. Okay, there are some words, if you use them: axis, inlet, wall, outlet. Fluent will understand it automatically and define and put the boundaries there. For example, this is my axis. I want to make Fluent understand that this is my axis, which is being revolved. What is revolve? Let me show. Pull. If you want to model this in 3D, let me show how to do it. You just put on pull. If you want to extrude it, you just do this, pull it. You just extrude it, okay, and put the dimension you need, 500. But I don't want to extrude this. This is a revolved geometry, okay? Is there any way to open and edit shape drawn in another program via ANSYS? Yes. You can import the geometry and open by space claim. You can open and edit shape drawn in another program via ANSYS. Yes. As I mentioned, you can import the geometry that's being drawn in other software and put it inside. How to do it? Let me show, just as the question came. You just put here, right click, then import. Here, where is the import? You should have import, but since we didn't import and we create new geometry, there is no there is no option here to have a import. But usually when you just, let's create a new Fluent, then right click, import geometry. I have marine structure step file. I can just import it and open it. Okay, so you just import it, then select the software that you want to. There are 3 modules for ANSYS. You can use Discover Geometry, CAD, Space Claim, or Design Modeler. But I use Space Claim. Others also useful. The others also are useful. Okay. Now let's get back, because we are like using our geometry. We model it. Let me show what is the revolve. Why this geometry is axisymmetric. Why it's axisymmetric. Let me show. Okay, you click on pool, then you click on the face, then you say, I want to revolve. Okay. After you say revolve, I think there should be like option of the axis. It should ask you about the axis. Sweep, draft, scale body. Okay. We just select the axis, then we return it. Okay, let me focus to show you. Okay, let's come back. Let's just zoom by scroll. If you press on Control and the cursor, so you can move it translationally. If you just click on the cursor, then rotate, spin it, so you can also roll your geometry. Okay, so we want to just look at like this side, what we are doing, how we revolve this geometry. You see? Okay, pull, click, revolve, then select axis. It needs an axis from you. You see? When you select the axis, it shows you. Okay, then you can also write the angle you need, like 50. So it will rotate it by 50. Let me write 300. Let me write 90 degree. Okay, so added 90 more. Let me say 50 more. Okay, 50 more. 50 more. Or from the beginning you say 300. Okay, let's Control Z. So you say 360. Then enter. You have a total pipe. This is the geometry that we have physically. You see, I mentioned it. This is the geometry that we have physically. But we don't need to waste our time. We don't want to waste our time in meshing a lot of elements, millions of elements. Okay, I just want to have 100,000 of elements. Even it's a big amount, but it's better than millions. Okay, so let's Control Z. I don't want to revolve. I just wanted to show the real geometry and why we put an axis. Why we name an axis? Because this is the axis of revolution. Physically, this is the axis of revolution. Okay. After we name it, where is the inlet? Let's focus on this geometry. Inlet is coming from here. Okay, it's specified. You can also have reading, understand what's going on here. It's very useful. I will also attach a link, so you will have access to a drive folder where I put everything here. Okay, we will have CFD course file. Every session we have, you will have Venturimeter, you will find my solutions, you will find some other papers. I will also like tidy these things up. I will tidy them and I will attach it as a link in the video description. Okay, so let's name this one. Let's say inlets. We can exceed 1 hour limit. I put 1 hour limit, but for this one, I mentioned some introductions, so you should consider that this session should be like 1.5 hours maybe. Outlet is also defined by Control G, same idea. Then I click on this, Control click, I keep clicking on the edges. I want to define these edges. Do you see that they are like walls here, where the fluid cannot, like because of the adhesive forces, the liquid will be like the liquid which is like the neighbor of the solid surface will be no slipping, will be stick on the surface, zero velocity. At the wall you have zero velocity, so you should let your software understand, or you should put this boundary condition as walls. So I define the walls, then I will click inside of the surface, and sometimes if it's a 3D, let me show. If it's a 3D geometry, let's say so you triple click to name whole entire 3D as a fluid domain. But now let me Control Z. My fluid domain is only a surface. only a surface. So I will name my surface as fluid domain. Okay, now we have a lot of things we made. We draw the geometry, we named the boundaries, we are ready to close. Okay. Don't need to save if you don't want to save it in other format or something else. You just can say close. If you are in the workbench environment, it will automatically be saved. So you can close it after you say file close. You can also close it from here. So now our geometry is defined. Okay, we go to mesh. We right click and we say edit. We start by meshing. Okay. And meanwhile, I can open COMSOL. Welcome to COMSOL. Actually, I really like this idea to have two software in one shot. Okay, as we say in Turkish, bir taşla iki kuş. Okay, so why? Because sometimes you want to learn like a new software, but you know the other one, ANSYS. So it's useful for you, or the case is good sometimes. For example, in COMSOL you find a good video, but you don't know how to do it in Fluent, right? So I want to do good examples, good tutorials. It should be useful for COMSOL users and also for ANSYS Fluent users. I want to let you aware. If you are a Fluent user, understand how COMSOL works. Maybe it's better for you. Because it depends on your application. I saw in some certain applications, for example, I'm now doing a PhD in chemical engineering. For me, I want to switch to COMSOL. It's better for me. But before this, when I was working in mechanical engineering industry, I don't need. I don't prefer COMSOL Multiphysics because I have heat transfer and fluid. I don't have something else to do. In multiphysics, if you have acoustics, if you have electromagnetics with fluid, so COMSOL Multiphysics is amazing too. So let me show. After you open the COMSOL Multiphysics, you say model wizard. Depending on your geometry, as I mentioned, it can also simulate 0D. Okay, it's not CFD, but it can also simulate it. But we will work on a 2D simulation here. Then let's close recently used. You will see a lot of things here. It's a good thing that you can do classical PDE modeling. So mathematical engineers or mathematicians or other applied mathematicians can also use this software. Structural mechanics, you have a lot of modules. You have semiconductor, radio frequency, RFM, electromagnetic waves, plasma simulations, optics. I like optics. Heat transfer. You have fluid flow. So this fluid and heat transfer similar to what we have in ANSYS Fluent. Electrochemistry, chemical species transport. If you have a reaction, then if you have acoustics also can travel in solids. So you hear this sound coming from the wood. So it can propagate on the solid. It can propagate in the air. So what you want to do? Aeroacoustics, or you want to have elastic waves, or acoustic structure interaction. So multiphysics inside of you have a structure and acoustics. And aeroacoustics also multiphysics. So I think it's very useful tool for multiphysics problems. Okay, but here we have only single physics. Fluid flow, I don't have porous media, I don't have particle tracing, fluid structure interaction. My case is single phase. Okay, creeping, laminar, turbulent, or it's a turbulent flow. Okay, we should check by calculating Reynolds number, but from reading the paper, the author also is using turbulent models. It's a turbulent flow, so you can just save your time and don't calculate Reynolds. Just go and simulate your case. Take K epsilon model and select add, or you can select K omega model or other solvers, turbulence models. But usually we use K epsilon and K omega in most of the solutions. When you get more complex problems and turbulence modeling is really important, you should get reading and how it affects. What is the best for my case? You say study. Okay, after we selected the physics that we need, we say, is my problem stationary or time dependent? So COMSOL Multiphysics starts by doing 3 steps at the same time. you see we have 3 steps here mentioned. Geometry, solar physics, you should define it at the beginning, you should decide. In ANSYS Fluent, you start by geometry, then adding your physics. In the Fluent itself, you should you just import the model that you need. Then you also start by like drawing your geometry. But in multiphysics, the way it works actually, it's a little bit like different than the ANSYS Fluent. You start defining your stationary or time-dependent solution. Actually, after that, you can change it. After that, when you open, you say that it's not converging in steady state solution. It's a time-dependent. I should solve it in time-dependent. Okay, that means transient. By time, it's changing. I should get at time equals to 0. What is the solution? At time equals to 5 seconds. Time equals to 100 of seconds. I should use time-dependent solution. Okay. And stationary. I don't know if I have a example of maybe here I have it. Let me show a transient solution to you. It's opened. Like we will make cross. Okay, let's open this velocity. Okay, this is when time equals. This is a greenhouse CFD simulation, 3D but time dependent. So time equals to. Okay, so we have slices. Okay, time equals to 470. Then you have 935. So it's time dependent and it gives you at each time. Okay. So, but in this case, in our problem now, we don't need that. We just have a stationary case. So let's go back to COMSOL. Let's say stationary. Let's say done. Then start to see the interface. But before that, let's jump into ANSYS Fluent. I have now two desktops, actually, one desktop and one laptop. I'm connecting by remote desktop to a desktop that is like 5 buildings away from me now. I'm at the library and it's at the office. So I'm like by using remote desktop, I wanted to like have ANSYS at that computer, solve the solution from there, and open COMSOL Multiphysics at my laptop here. Okay, so let's see what is the meshing. So our geometry is imported. It's okay. You see it. It's alive. Then we have named sections. They can be not here if you didn't name them from the cat. So I will delete them. I'm sorry to say goodbye to you. Let's say I'm deleting you because I want to show you how to name them by using ANSYS meshing part. Okay, you just right click on name selection and say insert name selection. When say name selection here, red section appears because you didn't select. You click on this, then it asks you to select the edge or something else. You can filter the selection here, edge, node. So I want to select edge. I click on this, so it will not see the faces or 3D solids. It will see only edges. So I click on this edge. You see it's green now. You can also zoom to see better, but okay, you can zoom. It's better to zoom. It's green color now. I say apply. You see its edge appeared that it's selected. So I will say I will name it. Okay, so it's a apply. Then you can right click and rename it. It is axis. I want to name it as axis. Then right click, insert name selection. So you can select this edge as inlet. Okay, rename as inlet. Then this we should select actually multiple. Let's say right click and zoom to fit. Let's select all wall edges. Control click. I think 1, 2, 3, 4, 5 edges should be included. But I will say name selection, then insert name selection. Then here it needs to select. So you say this one, control click, then click apply. 5 edges is included now. Okay. What COMSOL's purpose is actually? Emir, my dear friend, COMSOL is also CFD software. It's same as the ANSYS Fluent. Okay. But in some industries they prefer to use COMSOL, but some others ANSYS Fluent. Like as you have SolidWorks, CATIA, Siemens NX, you have Fusion, you have other softwares. So you have competitors also in CFD. You have Converge CFD, for example. It's very useful for combustion analysis in CFD. So if your company is a gas turbine engine manufacturer or designer, so you need to have Converge. Like it's very popular now to have Converge software. So let me name this as walls. Okay. Then I will name this part as, okay, I don't know what I did now. I created group by mistake. Okay, I will get back. I will rename it again. I created a folder actually. Let me. We named. Maybe we grouped them. Ungroup. Okay, ungroup is working now. Okay, let's deselect again. Just say apply. 5 edges are selected. Then rename it as walls. Okay. Last thing is just defining this. I did the same mistake. Let me say ungroup. Insert name selection. Okay, so now rename it as outlet. One thing, you should change the face. Like you are selecting edge, now you are selecting face. Then you should add another name to name the fluid domain. So this should be selected. One face is selected now. Rename it as fluid domain. Then come to mesh. So we will do meshing now. Okay, so how to do meshing? We have some, like at the beginning, you can actually meshing is a step-by-step troubleshooting process. Sometimes we need like several refinements. So like you should test. Sometimes you actually solve it, and you see that mesh is not good. You come back. So CFD is. This is why I said it's not easy to learn. It's always fails. Waste of time. A lot of waste of time. But I hope you enjoy this process. Okay, so you can insert multiple things here. Some things I didn't literally use them, but some parts of them is very commonly used, like sizing method or face meshing sometimes. Also inflation. Why inflation? You know that the boundary layer in a wall, let's say boundary layer, okay, thickness. So in fluid dynamics problems, you have this boundary layer, right? And there is a very small thickness that this shear stress at the wall propagates, that its effect stops. So after this boundary layer, this shear effects after this boundary layer is not included, okay? So you should this shearing effect at that boundary layer, you have high gradients. You should have very tiny layers, okay, to capture what's the inside of the boundary layer, what is the velocity distribution at that layer. So at the walls, and if you have external flow also, you need to have an inflation layer. So inflation mostly will be added. So you should select your domain, geometry, you select the face, then you need to select the boundary. What are the walls? So let's go back to the paper. Is this a wall? No. Is this axis is a wall? No. But only this part, you see the upper parts are the walls. So I go back and define the inflation layer walls will be this one. Actually, instead of clicking on 5 different edges, what you can do, instead of geometry selection, you can say, I want to say select named selection. I want to select something that I named. What is it? It is walls. So walls will be selected automatically without just clicking, because maybe there are like hundreds of edges you selected them, and they're all walls. So after name selection, you don't need to select them. You should just refer to name selection and select them. Now walls are recognized, but what is the smooth transition and what is the first boundary layer thickness? A good thing that when you go through the paper, you can find this useful information. You see here, layer thickness. Directly I found. Near wall meshing. Because author in the paper should mention this. This affects the solution too much. So should calculate or test and understand what is the layer thickness that he should use. So he says 0.0011 millimeter. But I not prefer to mimic or like emit, they use the same idea of the author here, even that it will give me the best result, but I have a limited time here. I have like a 1 hour challenge. Now we exceeded it, it failed at the first time because we talked about different things, but I want to have a 1 hour challenge. I want to finish quickly, so I don't want to waste time in some, even it's very important. If I'm doing a project now, saving time should be working in detailed way. So you should calculate Reynolds number, you should calculate the Y plus, what is my boundary layer thickness, what should I put as initial layer thickness. But for now, let's say smooth transition, let's have automatically calculate this boundary layer more easily. So let's put 5 layers. That means near to wall there will be 5 small dimensional layers, or let's say 6 thin layers. You can control it depending on, I said meshing is just troubleshooting step by step. You will see that now. Let's see, and you will understand what I mean. We will size it. I will prefer to size this geometry selection. I will select 3 regimes here, 3 edges, where we have velocity increase. We have the Venturi effect regime. So this I want to have at that selected parts. I want to have smaller elements. Okay, so I will select them, and I will define the element size. So you see now the current element size, I have only 6 or 7 parts, but I want to have better. So I can say 1 millimeter. So you see, I can zoom. So you see it's very close to each other. So 1 millimeter is good, and I go back to mesh. It's very big elements now, 58 millimeters. Okay, so I will let me be sure that our geometry is in millimeter scale. It's okay. It's 3 meters, I think. Yes, so should be okay. Okay, what we want to do now, to select a proper size. A good estimation to get your calculator. What is your area? Check your area. Let me check the area. Click on this. Face selected area has 3 point. Let us write this. 3.68 times to the 10 power 5 millimeters squared. If I draw squares, small squares inside, since it's 2D, there will be two-dimensional structures, two-dimensional shapes. Let's assume they are squares, and the element size is 2, so it will be 2 times 2. Let's see what is the number of elements. 92,000. So I want to increase, actually my capacity for elements of meshing for my RAM, I have 16 gigabyte of RAM. I can solve up to 4 million, I can say to the 4-5 million mesh. So depending on my capability, I can increase it and depending on the time that I want to waste for this, let's say 1.5. 1.5. I think 2 is also good. I think 2 is good because we are also using like fine elements here. We are using smaller size. Let's put 2 millimeter. Then see, maybe we need one more step. But let's say generate. Then it will start consuming some time. I will go to my COMSOL setup. You see something similar, but what COMSOL has, that you have the geometry modeling and physical modeling as one interface. So you don't, or also meshing in one interface. In Fluent, if you remember, let's go back to Fluent. Workbench. Geometry you do in space claim, then waste of time, you close it, you just open the meshing, you do meshing, then you go to setup. COMSOL is very nice in this like part, that you have only one interface, you do everything inside. But it's not that much good. In geometry modeling, you see it's not that much powerful to have complex shapes, to model complex shapes. So we will solve a similar problem, but a small geometry. Let's change to millimeter. I also need time to switch the COMSOL out. I'm not that much comfortable with COMSOL, but we can solve one problem here. So we will go to sketch and start like using some start modeling something. Let's zoom out. How I was zooming out. I want to zoom out. You can use this, but I don't remember what was the shortcut. Okay. Don't click on anything, just middle cursor, then you just zoom and zoom out. Okay. And right click, you can translate by right click. Okay, and left click, I think you can rotate, but now we are at the plane, we don't rotate. Okay, so we take a polygon, then click on the origin, let's say 300 millimeters. Okay, I have a rough sketch. Okay, I will simulate a rough problem here. Similar, even I will not like dimensionize it. I just want to quickly solve some problem to show how COMSOL works. But I don't want to spend too much time on COMSOL for this video. But in upcoming videos, I will include, maybe some videos will be more COMSOL focused, some other ones will be more Fluent focused. But we should have always 2 softwares in one video. Maybe I can delete this. I want to mirror this geometry. You can also switch, like you can shift before, because you didn't dimensionalize them. They don't have now constraint fixed dimensions, so you can change as you want. So now I added polygon, okay, from the sketch. Now I want to mirror this, all of the things. So you can come to geometry, right click and say transforms. You have multiple things here. So when you want to add something like circle, you can put the center and put the radius, for example, let's say 500, then build selected. You can have a circle here. So I think it's like wasting too much time to model, but you can understand by like similar to other CAD softwares, but taking more time. But for now, let's mirror this simple geometry. So transforms, mirror. Then you want to say select the input objects. Okay, it's recognized. Then you say build all objects. Now you see it's mirrored to because we didn't define the right axis. It goes to another one. So let's say 0. Normal vector is y-axis. I want to mirror it with respect to y. Build objects, mirrored very well, but I want to copy it by mirroring. I want to keep also input objects. So I click on keep input objects. When I say build all objects, these commands that I put will be executed. All commands is executed when you click on build all objects. If you just change something here, 5 or just say 1, and this is also 1, doesn't make sense. You should have build all objects. You see other, like 90 degrees also added in x-axis. I say 0, then I say build all objects. So you have the comment now. Okay, build all. There is no surface. There is no solid defined here. So I should have geometry, conversion, convert to solid. Then I select my object. Then I say build all objects. Now solid is totally defined. After I define this, I go to materials, but for now we don't need to add the materials. I will add the materials in the fluid properties part. You see, for user defined, I will say user defined. So we need only 2 properties. Why? More physics you add, more properties COMSOL will ask you. You added heat transfer, give me the coefficients. You added like electromagnetics, give me. You needed acoustics, give me the frequency, give me the conditions, give me this, give me. So depends on like like any property needed for that physics, COMSOL will ask you. For turbulent flow, we just need the fluid density and the dynamic viscosity. For the isothermal solution, temperature is not changing, but let's imagine the temperature is changing and we have polymer, which is viscosity is changing dramatically by temperature. So we should have materials, then add material from library, then let's say material library, it will load the materials, then you will have, let's say ideal gas, for example. Let's say ideal gas. I will add some ideal gas. Where was it? Elements. Okay. You can add hydrogen. Okay. You can add air or any other. Here it's like elements, but I think air is in other side. But here actually our problem is nitrogen based. Our field is nitrogen, but I want to use, because it's working in 60 bars high pressure, I want to know the properties. Now I should open. I want to know the density, for example, from the paper. What is the density that they used? For the first pressure condition, I will use this one, this simulation. They use 70.92. So let's go back to COMSOL. Materials, no need to define it there. If you don't want to call them in fluid properties part from material. When you say from material, you should have something inside. But if you don't want to call them from from the material library, you can just come to fluid properties, user define, and put the number that you have in the paper. The dynamic viscosity. The temperature is mentioned 20, so I go to dynamic nitrogen temperature viscosity, any database to call this paper. I think it's in the paper not mentioned, so I will use this value E minus 6 because it's 10 to the minus 6, so you put like this. So now materials are defined. When you come to turbulent flow, you can add the boundary conditions. I will add inlet. Okay, inlets are this one and this one, and velocity is 7 meters per second. I want to also right click and add my outlet, and I click on those and I say 0 atmosphere. Like here you have the 0 reference pressure, so that means like you have the atmospheric pressure. Okay, because the reference pressure here is set to 1 atmosphere, I think. Where is it? So reference pressure here is 1 atmosphere. So that means here you have is atmospheric, opening to atmosphere. But it's not the case. The physical problem that we have, it's like something else, but doesn't matter. For our case, we can just for now. Why I say it doesn't matter? Because it depends on the CFD simulation itself. Is it compressible or incompressible? You can have a compressible flow, but we are working with low velocities. You should calculate the Mach number. But here we know that it's like 7 meters per second. It's very low. So we have incompressible flow, okay? So because it's incompressible flow, we don't, like pressure does not make too much sense. Only pressure drop makes sense in the solution. Velocity, because the mass flow rate doesn't get affected with the pressure. So density is not changing. So we can just use 1 atmosphere for the reference and outlet is 0. Let me show you from paper why I use 0. Let's check the solutions from the paper. You see 0 is like orange, about the orange scale. Minus, you have positive, so orange like should represent 0, something near to 0. You see outlet is set to 0 Pascal, 0 bar as reference pressure. So same approach. I use the same approach. I use 0 Pascal. I have the walls. Let me check. Yeah, these are my walls I need. I have inlet condition, outlet condition. I have the walls defined. If you want to like delete something from here, you cannot delete because they should be like defined as something. If you want to, for example, define that edge as a different boundary condition, like open boundary is this part is open, for example, you should select and put outlet. If you have multiple outlets also you should select. But now this is the physical case that we have. Dimensions are not simulating the same case that we have in the paper, but I just roughly draw the shape and I want to just solve a solution here. I think it will not converge maybe, but we can solve it time dependent. If it's not converging in steady state, we can try to solve it in time dependent way. Like we are roughly doing like an exercise to understand the interface. So when you come to mesh, it's very good in COMSOL that you have a physics control mesh actually Fluent also has this feature, but I like it in COMSOL. It's I feel it's better. So you select fine or finer, that means the quality. It's normal is medium, then you can increase also. So let's say fine mesh, physics control mesh, it will understand boundary layers that I need to have like thin layers there. So it will help me to generate. I will say build all. So you see the mesh, like the quality that I need is generated. It's very nice. I should check how many elements that I have. I can say statistics, right click to understand how many. Okay, the number of elements is 24,000. I can increase them. I have ability to solve more mesh, maybe elements. So let's say finer. Let's say build all to have better mesh. Okay, that's good, very nice. Let me also plot the quality indicators. What is the skewness? Now I have high skewness regimes. Okay, let me check. Let me check the mesh statistics histogram. Oh, I have some bad actual regions, but just I want to skip. I don't want to waste too much time in optimizing the mesh. We can optimize it, but for now we just want to understand how it works. What are the steps that we need? Okay, just want to go quickly. Then after you define everything, you start compute. But I think I have an intuition that it will not converge, but let's let it start. So we will, I say that it's a long journey. We will start our first troubleshooting journey with you. So let's see if it's converging or not. So it started solving it. I will come back to ANSYS part and let's see what we do in ANSYS. Okay, I think we finished the meshing. I don't know. Okay, I open the mesh. How many elements of, okay, the meshing part is, you see, I have, okay, I switch from one software, I just forget the shortcuts sometimes. Okay, we have the boundary layer, you see, like more tinier. Okay, now I remembered how to do it. Okay, so you focus on the other part, like finer mesh, smaller than the others, as I want. Let me check some indicator, quality indicators, but let's check statistics. So I have 100,000. We can increase the mesh actually. To be honest, we can actually have better mesh. But you see, each step we refine it, we have time, we spend time, we do like, and also in the paper it mentions they use 600,000 mesh, I think, mesh element. From 100,000 to 1 million mesh they used, 1.3 million. But after that they optimize it to have 650. So that you see that you understand the paper author actually spent a lot of time in doing this simulation work, and we want to just mention a good, well-designed paper. You can read it, see the results, and we want to fastly get some, like reproducing some idea. We have the reproducing of the geometry, we reproduce the geometry, we try to mesh. We try to also solve the physically to get convergence, but let's see, like step by step, if we have a trouble in meshing, we can go back and mesh again. But now, I just want to check skewness and some quality indicators. Oh, skewness is nice, because the recommended skewness for ANSYS Fluent is about 0.49 or 0.94, I was thinking to say. 0.9 should be below 0.9. Okay, and our skewness is actually below it. So now it's trying to solve by COMSOL. Let's go back. So skewness is good. What about element quality? Should be more than 0.01. Okay, it's good. Okay, I will close. I check two element quality and skewness, quality indicators. You can also check other like aspect ratio. Let's check aspect ratio. Should be more than, like less than 7 or 10. Aspect ratio 1 to 5 is good. What is our aspect ratio? 1 to 5, but we have 9. We can optimize, we can refine it, but I don't want to spend time. I want to be a practical more. For now, just quickly get result. File and close meshing. We are ready now. Our meshing is done. So after you close it, you should say update. Okay, to transfer what you made, to save it, and you say update, then you go to setup. Let's see what COMSOL is doing. I hope it converts. I will be very happy if it converts. Now, okay, setup is ready now. Edit, okay. So let's say 5, solver process, double precision, and okay, start. Come back to COMSOL. We can also see the progress here. Oh, it's converged. I'm happy to have this result. Okay, you see the Venturi effect here. So velocity starts from the inlet condition that we put, 7, and it goes to, let us see the velocity here. It goes to like about 12 to maybe 15 meter per second. Then it expands again and reduces its velocity. And you have some vortices here. We can have more smoother transition. Actually, let me see if I can show you the vortices. Velocity, I want to see streamline. And let's say plot. Let's put more. Plot. Warning. Why is giving warning? The plot is empty. Okay, streamline. Maybe we didn't select from parent. Yeah. Velocity. From parent. UV on selected boundaries. Still we have warning. Let me check from parent. Let's say again. I think this is the way. You get just right click, streamline, then X component U, and this is V. Let me see. From parent, expression. Study one solution. If we say solution, okay, let me check results. 2D plot group. Entire geometry, okay. But we should add something. Surface. Okay, I want to say plot. Okay, so you just add 2D plot, then add a surface, so it will give you the velocity gradient, okay? The velocity contour. Then, if you want to see the streamline, should be okay to have plot. I don't know why it's giving an error. Title, automatic. I'm not that much familiar. Disable, let's say plot. Tile geometry. Okay, I want to show you the... I'm not able to do it now. I also switch from one COMSOL version to new one. Now I will figure out what is my mistake. Okay, you should have also contour here. But let's say delete it. Okay, we have the solution now. Let's see the pressure. Pressure has the contour. 50. Okay, let me try here to have contour. I will delete this. Add the contour. Okay, we can see. Okay, now we can see the vortices, but I will increase. Okay, so this like blue stagnation point, 0 points, should be the vortices side. Okay, as I mentioned, we can reduce or eliminate these vortice regimes by smooth transition. We have a sharp edge here. We can have a smooth transition to don't have those vortices at the blue sides. Like blue 0 points indicates that there is like energy loss. So you should change your geometry if you want to optimize it or something else. Okay, let's go to ANSYS Fluent if we have something. Okay, now we just set up something similar here. We should have axis symmetric here. Our case is axis symmetric. Check. Meshing is checked now. Okay, you just open general and check mesh. Pressure based. Our solution is pressure based, density based, usually the supersonic simulations. It's a steady state problem. Material, let's define our material. New material. I will say nitrogen. Nitrogen. And here chemical formula also is nitrogen. Okay. The density was 70 point. 9 to 1, and the dynamic viscosity is just, I think, yes, 10 to the power minus 6. So change and create, you say, then overwrite, you say no, I don't want to delete air. So it is saved now. You can see it, that fluid materials, you have nitrogen. Double click to see if it's okay. Yes, density and viscosity are defined well. After you put this, now step by step, actually, you follow this like window, step by step, you should define everything carefully, starting by check. Then what is the physical model you need? Is it multi-phase? No, we have single phase. We have isothermal problem. We don't need to simulate heat transfer. If we open it, we need to define temperature boundaries, we need to find heat flux boundaries or insulated parts, or we have radiative heat transfer or like convective flux at any boundary. So it's a different problem, okay? We don't need it. So viscous model is the single phase fluid dynamics part. So I should have a viscous model, turbulence model that solves this problem. So let's say K omega is nice for this problem now. We don't change anything. Our turbulence model will be K omega, and we say okay, and we don't add anything. Our model is nice, just close it. Materials also defined. I showed how to add it, nitrogen. Motion definition, no need for this case. Fluid. Let's open cell zone conditions. What fluid domain means? We define it. We just actually named the fluid domain. Let's see if it's correct. Click on this mesh, spherical mesh. Then we just click on the selected parts. We say display. Okay, walls are here. We can display anything we need. Outlet is there. Okay. This depends on the named selection that we made in meshing and in geometry. Interior fluid domain. Okay, my surface is this fluid domain. Axis will be at the bottom. Inlet will be at the left side. So, depending on your definition of the names in the mesh part, Fluent will automatically recognize them. Okay? You should name them at meshing. Without naming them, you cannot name them here. Only specifically named parts will be imported to Fluent solution part. Fluid domain edit. Because I want to change my fluid. It is air now. I have nitrogen. Apply. Now it is changed to nitrogen. This is what you need in cell zone. Because you have a fluid zone, what do you have in the fluid zone? Is it water? Is it air? If you have multiple zones, let's say we are also simulating the solid part. We have a heat transfer problem. Heat transfer problem can have this convective heat transfer inside. You have a fluid, then you have a solid heat conduction, heat transfer, then you have outside air. So you have T infinity here, T infinity outside. You have a heat transfer problem now. And sometimes you have insulation layer here. Okay, so let me show insulated pipe. Like it's morely like very widely used in like air conditioning pipes, ducts, because we are carrying a cold or extremely hot fluid, we should insulate it. So it's a fluid dynamics heat transfer coupled with fluid dynamics problem. So sometimes we want also another domain. We should draw this solid geometry and we will have another cell zone in our problem. We should have another cell zone and we name it as solid. And we select aluminium or copper or PVC, anything. So in this problem we have only one domain, one fluid zone. So we defined it, we are done. We go to boundary condition, X is already defined. Inlet, you can click on it and edit. Velocity inlet is automatically recognized. You can change it if you have mass flow rate. You want to define mass flow rate or pressure inlet or something else. But velocity inlet and mass flow inlet is the most common things that we define and most robust in terms of numerical solution. If you put pressure inlet, pressure outlet, not converging. Most of the times cannot converge. Velocity magnitude is 7. Apply. Close. Outlet. I do this. I use this software for a long time, but when I define, I want to be sure. Come back and apply again. Internal fluid domain is okay. Outlet, I will check it. 0 Pascal, okay. So we say it's like going to reference pressure. Pressure drop will be like the outlet pressure is 0. So inlet pressure, let's say 1000 Pascal. That means pressure inlet is not given now. It's not input. Fluent will calculate the pressure inlet. Okay? We not define it. We don't define it. After the software calculates the pressure inlet, we understand the pressure drop. If it gives you 1000, so that means you have 1000 pressure drop. This is why we use reference pressure of 0 Pascal to directly understand pressure inlet related to pressure drop. So let's say, okay. Some other things you can also search. You can just take this screenshot, ask ChatGPT or any AI tool to help you understand like each parts here. Or you go to manual PDF of ANSYS Fluent. Open this. There are a lot of useful information. Okay, you can open this. You can open ChatGPT and use both of them. They are guides, Fluent user's guide. You can check meshing mode, solution mode. I have a problem in solution. What should I do in like modeling turbulence? Which part I should say? For example, K epsilon we selected, right? Or K omega, I don't remember. But so you see a lot of useful information here. It will guide you. So keep in mind that you can use ANSYS Fluent solution manual. We always prepare for exams. Always I say solution manual. So it is user manual. Okay, user manual. Yeah, let's check the walls. Edit. Walls should have no slip boundary condition. In some specific applications, you can have moving wall, and also you can have a shear at the wall. You can have a shear. Like sometimes the no slip boundary condition is not the physical case of your problem. It's very deep topic where there will be a no slip. Okay? In some cases there will be no slip and you should specify the shear. But in our case it is no slip and stationary wall. Is our wall moving? Let's check. There are flanges and it is fixed, right? So no moving wall, just stationary wall. Apply and go away. Everything is nice. We finished setting all physical case. All physical setup now is done. Let's go back to presentation. I show that solvers has different methods, and also let me show from other slide, maybe this one. Okay, are you using simple like piezo or coupled? Like what is this, implicit or explicit? You will find these useful things in ANSYS Fluent inside. So it is defining. You can have methods. You can change like coupled. You can change it to simple. Okay, let's say coupled. And second order, you can change it to standard or linear. Okay, so we solve this second order upwind. It's a robust solver, but depending on your case, I'm also not that much I don't have too much knowledge in the solver setup, but I can say that, like for example, second order upwind, I remember from an assignment of course that we took, this one for example, some problems, like let's say low Reynolds number regimes, you cannot solve it by some solvers, will not converge. You need to do something else. So what you do, you change the numerical algorithm. You switch it to something else, like what I mentioned, second order upwind, but other, like rather than using something like worse than this, so it will converge depending on the selection. So this also makes sense that you should have a good control and method algorithms. So this is like relaxation factors, means in the numerical solver, a coefficient that is being multiplied in the boundary in the governing equation that you have. So it's like it's a tool that helps to faster convergence. Faster convergence. If you have a relaxation factor, you have a faster convergence. You can change the contribution level of each solution part. So you have pressure, you are solving pressure, momentum equation, you have like band density, other kind of things. Turbulent, you are solving the turbulent, like Reynolds average. You have a turbulence model, right? You have the K epsilon, K omega. So you have also turbulent kinetic energy plays role. We don't change them. Just I want to mention. Go to initialize. Say hybrid initialization, initialize, it will initialize your step. And if it's going well, here you see iteration 1, it gives you the error. So error is 1 to the power minus 0.6. If you have no idea about numerical methods, you can watch our video series, Turkish Engineering it's in Turkish actually. I recommend it for okay, it's applied numerical solutions. So you will see in my lecture series, numerical solutions, numerical methods. It's an undergrad level course. You will see something related to initialization and error. This error you see when you solve a numerical problem. Actually, our lecture series are very simple to follow. Very simple questions, mathematical questions we solve numerically. Then at each iteration step, we evaluate: are we converging? Are we getting better, lower error or bigger error? So now you see we are going to lower values, 10 to the minus 8. So at the initialization, sometimes you have divergence at the first 10 step. So you have some unphysical, you have something very bad if it's diverging at the first steps. If it's going well, you are okay. You say run calculation and you select number of iterations depending on your assumption. I say like 200 steps will solve my problem, like we converge. I hope, inshallah, that it will solve. And I say calculate. So other things I don't change. I just change the number of iterations. Okay, let's say 199. Then I say calculate. So it will start solving my problem. And you can monitor your solution, how it goes, by the convergence, like iterations and the error, like showers here at the other axis. So it should go down. It should go down and converge. But if it's numerical, if there is a mistake in the mesh, if there is a mistake in like unphysical case you defined, it should not converge. But I'm happy that alhamdulillah it's going good now. So let's see if it's converging, if it's going well. Let's see COMSOL. Let's see our friend if it's comfortable. I think everything is nice. We solved it here. We can do some post-processing, but as I said, you can have like 2D plot and you can see, let's say 1D plot, or no, I want to see like how velocity changed by x-axis, but still I need time to learn post-processing here to have better post-processing. But okay, we need actually the velocity contour and pressure contour, the most critical things. The other things, other parts of post-processing, we will do them in other videos. But for now, I'm happy that we like modeled a geometry and solved a complete COMSOL problem. Go back to ANSYS. Alhamdulillah, calculation complete. Thanks God that it's complete. So you can now see what you want to see. Come to graphics, contours, and say new. I want to see pressure. Where? In my fluid domain. I say display. You see the pressure. And I want to see, let's say, close and add more contour. Now a contour is added now. I add more contour. I say velocity and interior fluid domain, save display. You see my, now it's like, what I want to say here, this is the axis symmetric problem, so it should be mirrored to the, you can do it in post-processing, but let me show you how should it look like, okay? But we can do it in post-processing, but now in a primitive way I will do it, okay? By PowerPoint. The solution actually, it gives you just only half. It is just, say rotate, okay. So this is the solution. This is the 2D pipe. You have the velocity increase here, then it's going like this, okay? This is our solution. Let's compare our solution to the paper that we read, okay? The conditions that we used is the first solution that he made here. Velocity that he gets at this part is 21.1. And the other cases, we didn't simulate them, but we only simulated one case. So you see 21.6 meter per second, 21.6. We are like kind of qualitatively good agreement with the, like we finished the simulation and we have something similar to we have like converged simulation, and we like solved the problem and got the contours, and comparing to his solution, I think we have good agreement. Let's see the pressure inlet that he calculated is about. We should also take averages, because of like only by seeing the contour you cannot evaluate. You should have some calculation reports. I can show them, but basically we can just get a quick idea of the pressure here. Let's see his contour. Compare this our simulation by this one. You see a good agreement. Okay, you see a good agreement, and let's maybe get a bigger size. 1.38. Okay, let's convert it to bar. 1.38 10 to the power 3, then divided by this is Pascal, so 100,000 will be bar. So in bar it is 0.0138 in bar. So 0.17, we have 0.3. Yeah, actually this is not a good way to evaluate, because you should take the average, but I'm just checking qualitatively what we get, and like this is the way to do that. But you should you should solve the same problem by more finer mesh, by better mesh, or by lower mesh also. You should compare how is my solution changing, and to have like good. And also you should check with the experimental results. You should compare. For example, this guy compared his Venturi test from CFD and from experiment. How much agreement have? Only 0.9 error by percent. So 0.9% means like approximately 1% only have error between them. It's a very good agreement. So I think we finished 2 simulations, and my challenge is failed in terms of 1 hour, but because it's a first introduction to the 2 softwares, 2 CFD softwares, so it needs time to like introduce them. For the upcoming session, let me also mention in the like flowing of our lectures, I will complete to add these screenshots to have a good tutorial for you, tutorial manual for you, and upload in as a drive link at the description. So you will have like screenshots of how we define the problem, but also you can just see the recording because it's recorded. Okay, let me mention the plan of the live sessions. This tutorial series, inshallah, will include different physical problems. We start by single phase simple problems, then we add more and more physics. More and more I learn, more and more I will try to transfer. I'm still a self-learner, trying to explore how CFD is amazing, how we can do good stuff with it. So I will try to have more and more examples. So upcoming lecture will be in orifice meter. So we will simulate orifice meters similar to Venturi, but you see a sudden decrease here. There is no transition. A sudden decrease, and you have a lot of vortices. So this is orifice meter. More energy lost, but it's also a way to evaluate by the pressure drop after orifice meter. You can also measure the flow rate. So this is our second example will be, inshallah. We can have pipe heat transfer. I want to also quickly introduce how to use fluid dynamics with heat transfer problems. So after 2 videos, you will just jump into multiphysics, heat transfer with fluid dynamics. Then we have coil heat exchanger CFD analysis with airflow, and we have coil. So maybe here also I will show, I still need to work, and maybe we can also find a paper, experiments, and we try to simulate experimental condition. So I need time, but as I mentioned, I plan to have a video per 2 weeks, or like sometimes 3 weeks or sometimes 1 month. We have a ball valve analysis. giving my experience in valve design and like simulation. So I want to also include some like very standard valves. They are very standard, not complex physics inside. Very standard valves, just cross-section area is decreasing and you just change the flow rate or something. So ball valve will be also our case. Then von Karman, this is low Reynolds number instability problem, von Karman vortices. It's a very nice visually. So we will simulate this solution. Then we have more and more, inshallah. So we have like CPU cooling, electronic CPU cooling we can do. We can do electric motor cooling problem. We can do a lot of cool stuff together. I hope you like, and if you like the video, please subscribe and press on the like button, because we need to get your feedback in order to work more and more and encourage ourselves to do new videos. So I hope to see you in the next session. Thank you so much for watching, and see you. Assalamu alaikum.